Okay, you guys, now we're looking at distributed loads by integration. So we're working with the two first examples we had, where we had this distributed load of 200 pounds per foot spread over 4 feet. And we also had the distributed load triangular spread over 4 feet, where it's 0 at one end. And then at the other end, it was 750 pounds per foot. So let me zoom in a little bit. Okay, the first thing we know is that we know in order to calculate the force, it's 200 times 4 feet. So it was 200 pounds per foot over 4 feet. And we learned that it was 800 pounds. Okay, and that was by doing the area. Well, what we could have also done is do force is equal to, the force is equal to a segmental part, remember from integration, where dF is really the portion of the force is equal to W times dx, because we're looking at it, incremental piece of the force is equal to incremental piece of the dx. So if I integrate both sides, the force turns out to be the integral of W dx. Okay, so let's do that. The force integral from 0 to 4 of W, which is 200 dx, it turns out to be 200x going from 0 to 4, and it turns out that F is equal to 800 pounds, which matches what we got up here. And of course, we'd have to put in the negative, right? Because we're looking at the force going down, right? So I'm going to have to put a negative in here, a negative, and get a negative. So the same step with the other is F is equal to the integral of W dx. Well, in this case right over here, I knew that the equation of this line with the y-axis being the W line, the integration, this line is 200. But in this case, on the triangular one, I'm looking at a line that's like this, so I have to find the equation of that line. So equation of that line, let's do that first. And I'm going, I think, much slower than you guys could do. So y is equal to mx plus b. M is the slope of this line. What is the slope of this line? It is the change in y over the change in x, so that's 750 over 4x, and the b-intercept is 0. So the equation here is y is equal to 187.5x. That's the equation of this line right here. Y is equal to 187.5x. And then I know the force is equal to the integral of W dx. So the force turns out to be the integral from 0 to 4 on 187.5x dx. So F is 187.5x squared over 2, going from 0 to 4. And the value turns out to be sorry, I have to zoom out so you could see it. So F is equal to 180, the integral 187.5 x dx, x squared over 2, and it turns out to be 150 pounds negative, which is what we found when we just did the area. Okay, so whether we're doing by, basically, I guess what I showed you before, the reason why you could just calculate the area under each one is because the area is really the integration under a line. And in this case, we have the integration of this line. We have the integration of this line. It's actually the integration of anything. It could be a curve. But I basically was able to find out what my force value is. Okay, now, next. We know the moment is F times the distance. So the moment is equal to F times dx, which means F, we know from up above, F is Wx. I'm going to put Wx dx. So I basically have the moment is equal to Wx. Sorry, I forgot to put the Wx dx. So the moment is equal to the integral of Wx dx. So in this particular case, the moment for this problem, the integral from 0 to 4, W is 200, x dx, so it's 200 x squared over 2 spread from 0 to 4, and the moment turns out to be 16 divided by 2 times 200, 1600. And the units are foot-pound. So if we know what the force is and we know what the moment is, we could find what the perpendicular distance is. It's the moment divided by the force, and the moment is 1600 divided by 800. So from here, I'm coming up here, which equals 2 feet. So what did I just do? I solved for the force by integration. I solved for the moment by integration. And then I found the perpendicular distance, which is really our centroid, by dividing the moment divided by the force, and it turned out to be 2 feet. So just as a 200-pound distributed load per foot, a 200-pound per foot distributed load spread over 4 feet, the equivalent force is 800 pounds going down, and the distance, or the centroid to that point, is 2 feet. And I determined it by figuring out the integration to determine the force via integration, and then determine the moment via integration. So going back to this problem, same kind of thing. I found the force already, and now I know the moment is equal to the integral of Wx dx. And W in this case, W in this case is 1875x times x dx, and I'm going from 0 to 4, 187.5 x squared dx, so it's 187.5 x to the third over 3 spread from 0 to 4, and the moment turns out to be 400 foot-pounds. And again, we're looking at this as got to be a negative value because my force is all going down. Same thing with the left one. And then the perpendicular distance is the moment divided by the force. So that's 4,000 divided by 1,500, and 4,000 divided by 1,500 is 2.67 feet. So instead of just calculating the area, if you want to do it by integration, you can. And now I'm going to do an example that's not a distributed load, that's either a triangle or a rectangle, but I'm going to do an odd shape. So I'll be back in a moment. Okay, so now I have a distributed load at a certain shape, and I'm given the equation of that shape. It's 200x minus 25x squared. In this case, I don't know where the centroid of this is. Maybe I'd be able to figure it out in some capacity. But in this particular case, I'm just going to do it all by integration. So the first thing that we know is the force is equal to the integral of W dx. So the integral goes from 0 to 4, and W is 200x minus 25x squared dx. So it turns out to be 200x squared over 2 minus 25x to the cube over 3, and that's all over 0 to 4. And my force, when I do my math, my force turns out to be 2,667 foot-pounds, and again, it's negative. Then I solve for my moment. My moment is equal to the integral of Wx dx. I'm going from 0 to 4 again. 200x minus 25x squared x dx, which is 0 to 4. 200x squared minus 25x cubed dx turns out to be 200x cubed over 3 minus 25x to the 4 over 4, going from 0 to 4, and the moment turns out to be, the moment turns out to be 2,667 foot-pound, and the moment negative. The force, I did the math wrong. It's 1067. So if you checked me on this, it was 1067. And then I did the moment. So now the perpendicular distance is going to be equal to the moment divided by the force, which is 2,667, 1067. And it turns out to be 2.5 feet is equal to our perpendicular. So I bet that if we had known what a centroid is, a parabola, we would have been able to figure it out without even doing all the integration. But in this case, whenever you have a shape that you don't know where the location is, you could calculate your force and your moment using integration and then solve for the perpendicular distance. Okay. I'm going to stop here now. So just go on and do the distributed load homework now.